All right, this is exam 2 for physics 101. This chapter is second part, chapter 4, 5, 6, and 7. When a car's tires are rolling, which of these is the type of friction between the road and the tire? And as long as the tire is rolling, it's going in this direction, the type of friction is static friction. It's only when the tire stops rolling, when it skids, that kinetic friction is relevant. So A is the answer. Mass of 2 kilograms sits in an inclined plane as shown here. What must the force on the block be for the accelerate up the plane at 5 meters per second squared? All right, first let's just draw our forces. I have FW, I have FN, and that's all. Now we'll draw our coordinate system. There's my x-axis, there's my y-axis. This angle is 30 degrees. I'm going to go ahead and draw this. I'm going to go ahead and actually resolve the force vectors when I do this. So I have Fn here, I have F, and then I can resolve my force weight into its components. That's Fw sine of 30 and Fw cosine of 30. All right, now I'm looking for F. So I say the sum of the forces in the x direction, that is going to be Fw cosine 30 minus F equals ma. And then I solve this for F. Fw cosine 30 minus ma, and then I put in my value. So I have 2 kilograms times 10 cosine of 30 minus 2 kilograms, and this is the part that a lot of you miss. It should be negative 5 meters per second squared. Negative 5 because it's accelerating in this direction, which is in the negative x direction. I solve for F, and I get 30 newtons. Let's see. What's the normal force? Well, we just look at our y vectors right here. Our normal force is equal and opposite the force weight sine 30. So that is our normal force. D is number 3. What happens to the normal force acting on the inclined plane as the angle theta is increased? Well, if I have an inclined plane here, theta, if I increase that theta, that's Fw sine of 30. Now 30 isn't theta. Remember, this was 60. But if I increase that, that makes this angle go down. And as that angle goes down, the normal force also goes down. All right, so the normal force decreases. You can think about it too. The extreme, when it's all the way up vertical, the normal force equals 0. It goes to 0 because it's no longer touching the surface when it's vertical. All right, rope box weight. 100 newtons is resting on the floor with mu s equal 0.5. Have a tension of 30 newtons. Which way does the box move? Well, first let's figure out what is the static frictional force. That's equal to mu s times the normal force. That's 0.5 times 100. That's 50 newtons. That means that that's the maximum static frictional force. That means that I need to exert at least 50 newtons to make it move. As it is now, I have 30 newtons for my static frictional force in that direction, and so the box doesn't move. E. Box is being pulled across a rough floor at a constant speed. What can you say about the work done by friction? Friction does negative work because the displacement is in this direction, but the frictional force is in that direction. So they're opposite directions, that's negative work. How does the work required to stretch a spring 6 centimeters compare with the work stretched at 2 centimeters? Well, potential energy of a spring, potential energy of a spring is 1/2 kx squared. I'm increasing this by a factor of 3, so that means that it's going to be 9 times. I don't know what happened here, but it's 9 times as much work to stretch it 6 centimeters. To stretch it 3 times as far requires 9 times as much work. Oh, sorry about that. Something happened. All right. So this block at rest on top of this frictionless inclined plane. What is its speed when it reaches the bottom? All right. Well, up here it has potential energy, and the kinetic energy equals 0. And then down here it has kinetic energy, but the potential energy equals 0. So we say the potential energy at the top plus the kinetic energy at the top equals potential energy at the bottom plus the kinetic energy at the bottom. Some of these go to 0. I get mgh equals 1/2 mv squared. Masses cancel. I'm solving for V. That's what, root 2GH, which is the root of 2 times 10 times the height, which is 3 meters. Square root of 60, which is roughly 8. Yeah, so 8, 7 point something, but it rounds off to 8. All right, so B is the right answer. Imagine the inclined plane has a frictional force acting on the block. The force is 2 newtons. What energy is lost after the block has moved down the inclined plane? All right, so as it's moving down, I have a frictional force equal to 2 newtons. All right, so this block is moving in this direction, but it has a frictional force acting upon it. So that frictional force does a certain amount of work, which is Fk times d. That's 2 newtons times the distance d, which is 5 meters, which you can find in a couple of different ways. First, you could just say this is a 3, 4, 5 meter triangle. Or you could say the square root of 3 squared plus 4 squared is equal to 5 meters. So you need to know the distance from here to here, because that's the distance over which that force acts. And once you find that 5 meters, you find that it loses 10 joules of energy. So the 10 joules of energy is lost. And then I want to know, what is the kinetic energy at the bottom of the inclined plane? Well, the total energy at the top is just the potential energy, and that's mgh. Was it 2 kilograms, I think? No, a 10 kilogram block. So that's 10 kilograms. It's 10 meters per second squared times 3 meters. That's 300 joules. But then it loses 10 joules of energy. So 300 minus 10 equals 290. D. 11, a guy pulls a block 5 meters across the floor as shown. What is the work done? All right, well, work is just FD cosine theta. That's 30 newtons times 5 meters. It's cosine of 60. That's 150 times a half, which is 75 joules. All right, so let's look at the next one. For the previous problem, what is the normal force on the block? So let's just take a look here. I'm going to erase this. I want to find my normal force. To find my normal force, it's going to label all my forces. I have my normal force, I have this force, F, and then I have my force weight. Now, normally, your normal force would equal your weight, but in this case, that's not true, because we have this extra force. We have this force F at 60 degrees, normal force, and then my weight. And I'm going to resolve that force vector. So let me do some different colors here. So here's my coordinates, and then my normal force, Fn. I have my force, F sine of 60. And I have F cosine of 60. And then I have my weight. If I look at the sum of the forces in the y, because that has my normal force in it, that's going to equal F sine 60 plus Fn minus Fw equals 0, because it's not accelerating in the y direction. And so Fn will be Fw minus F sine of 60. That's 200 newtons minus F, which was 30 sine of 60. Uh, 174, rounding off 170 newtons. So that's my normal force, is 170 newtons. That was answer A for number 12. 1 kilogram block is traveling to the right at 3 meters per second. Collides a stationary 2 kilogram block, and the two blocks stick together. What is their final velocity? All right, so I have an initial and a final state. My initial state is I have a 1 kilogram block moving at 3 meters per second. And the 2 kilogram block has 0 velocity. This is my 1, this is my 2 kilogram. And then afterwards, they stick together, and they have some velocity. I want to know what that is. Now combined, these have a mass of 3 kilograms. All right, so my initial momentum is 1 kilogram times 3 meters per second. That has to equal my final momentum, which is going to be 3 kilograms times the velocity. So 1 times 3 equals 3 times 1. Velocity is 1 meter per second. That's B. Which of these statements is true? Well, let's see. Energy is a scalar, momentum is a vector. So that would be B. Two boxes, one heavier than the other, initially at rest on a horizontal frictional surface. Same constant force acts on each one for exactly 1 second. Which block has momentum? I know that F equals delta P over delta T. I have the same force acting for the same time on both objects, so they both have the same change in momentum, delta P. All right. Alex throws a 0.15 kilogram rubber ball down at the floor. The ball speed just for impact is 6.5, and just after is 3.5. Ball is in contact for 0.025 seconds. What is the magnitude of the average force? All right. F that I know from Newton's second law is delta P over delta T. So I have this ball. It's traveling downward at negative 6.5. And then it comes up and it bounces back upward at positive 3.5. So to find my force, I first find my change in momentum, which is going to be the mass, times Vf minus Vi over delta T. It's going to be 0.15. Vf is 3.5 meters per second minus a negative 6.5. That's my initial, which was in the negative direction. So if you miss this, you probably got your signs wrong here. Over 0.025 seconds. And so that's 0.15 times 10, which is 1.5 over 0.025 is 60 newtons. So B is number 16. 75 kilogram swimmer dives horizontally a 500 kilogram raft. So I have a raft, swimmer on it. Initially, the momentum equals 0 because neither one of them is moving. But then the swimmer jumps off. He goes in that direction. And so the raft has to go in the opposite direction. So we say PI equals PF. That's 0 equals the momentum of the raft, which is going to be the mass of the raft times the velocity of the raft, plus the momentum of the swimmer. Looking for the velocity of the raft. Velocity of the swimmer is 4 meters per second. And we solve for VR. And that is equal to, let's see, I think it's 0.6. Yeah, 0.6 meters per second. That's B. Which of these collisions is momentum conserved? Momentum is conserved in all collisions. So all of these things. Energy would be preserved only in the gas particles colliding. But momentum is conserved in all collisions in the universe. An elastic collision is one in which both energy and momentum are conserved. So those are collisions that involve field forces. Bonnie sits on the outer rim of a merry-go-round. We have a merry-go-round. Bonnie sits here. Clyde sits here. Who has the larger tangential velocity? All right, well, they're both moving around at the same omega, the same angular velocity, but Bonnie's covering a greater distance in the same amount of time, so she has the larger tangential velocity. Object begins at rest, rotate with constant angular acceleration. It rotates to an angle theta in the time t. What angle did it rotate in the time 2t? I know theta equals omega naught t plus 1/2 alpha t squared. It's at rest, so omega naught equals 0. So if I double my time, I quadruple my theta. If I double this, since it's squared, I get a 4 theta over here. So E is the right answer. Fan in this picture is rotating in the direction of the arrow. Rate of rotation is slowing down, so this is omega. Since it's slowing down, I know that alpha is opposite omega because it's slowing down. This omega is clockwise, so that is in the negative direction. That means that alpha is positive. It's opposite. All right, that's 22. A few more. A fan blade initially at rest rotates with a constant acceleration. Let's just write down everything we know. Omega naught equals 0. Alpha equals 0.025. And what is the time interval for it required to reach 4.2 radians displacement? All right, so I say theta equals omega naught t plus 1/2 alpha t squared. Omega naught equals 0, so that goes away. That's good because it makes it a lot easier. 4.2 equals 1/2 of 0.025 t squared. So t is the square root. I get 18 seconds, so 23. Oh, let's see, 4.2, 8.2. Yeah, I get 18 seconds. So 23 should be A. All right, a Ferris wheel initially rotating at an angular speed of 0.5 radians per second. Omega naught equals 0.5 radians per second. Accelerates over a 7-second interval at a rate of 0.040 radians per second squared. What is its angular speed? So I want to know what omega final is, excuse me. What is omega? I know that omega equals omega naught plus alpha t. And simply just plug it in, so I have 0.5 radians per second times 0.04, or excuse me, plus 0.04 times t, which is 7 seconds. I get 0.78 d, 0.78 radians per second. And now finally, 25. The distance from the center of a Ferris wheel to a passenger seat is 12 meters. There's my Ferris wheel. This distance from here to here is 12 meters. What centripetal acceleration does a passenger experience when the wheel's angular speed, that is omega, equals 0.5 radians per second? All right. Well, my centripetal acceleration, AR, is equal to v squared over r, but I also know that v is equal to omega r, so I can plug that in. I get omega r squared over r, which is omega squared r. So I have an alternate expression for the centripetal acceleration, omega squared r, and that's equal to 0.5 squared times r, which is 12 meters. So that's a quarter of 12. Should be 3 meters per second squared. So 25 is D. That's the end.